yesterday's discussion. Yesterday we discussed about the static determinacy and indeterminacy of truss system. Okay, the simple problems. We saw that static determinacy and indeterminacy can be found by the simple formula m plus r minus twice j, where m is the number of members, r is the number of reaction force, and j is the number of joints in the truss system. Now this was valid for a 2D system. Now if in reality we have a 3D system, then that 2j will be 3j, simply because now it is a three-dimensional truss system and there will be three components of the forces. So in the x direction, y direction, and z direction. So at every joint, we will be able to write summation of forces along x equal to 0, summation of forces along y equal to 0, and summation of forces along z equal to 0. Earlier it was like this, along x and y. Now another third will come if it is a three-dimensional truss system. Now after that, little bit of member force. What happens inside the truss? So the truss system will be used in bridge, maybe in a railway bridge, steel truss will be used, or maybe in industrial buildings. So these are two very common examples where truss systems are going to be used. So we know the external load, okay? The external load that will be coming onto the truss system, we will know. How? Because when we are designing the bridge, we will know what type of vehicle will be moving through the bridge. We will go for the maximum intensity of load that the bridge can bridge may have to face in its lifespan. Okay, so that load we will take and we will apply in our analysis. If it is a roof system, then we will analyze the forces coming on to the truss system from the dead load of the roof, from the imposed load, if any, from the wind load, and other types of load, if any. Now, by this time, I think we know what are the types of load. There were some types of load we discussed: gravity load in the direction of gravity. Those will be dead load, live load, imposed load. There may be other type of load like snow load, etc. And there may be horizontal type of load, mainly earthquake load, wind load, etc. And there may be some other types of load also, like hydrostatic load, then hydrodynamic load also may be there. Like this, there are different types of load. Hydrostatic load will come when the load is coming due to water, which is in static condition, okay, still water, like a reservoir, okay, water is stored and then the load is coming onto the structure. These are different types of loads that we have, that we should know and we should be familiar with. Now coming back to the truss system, so what I'm going to say that we will know whatever the external load is coming, or we have to find out for the purpose of designing the truss system or the structural system. Now, whenever the load is coming, for example, if this is a truss system and the load is coming here at the bottom chord, then what will happen? Maybe this will try to go like this, maybe because the load is coming in that direction of gravity, and therefore in these members, there will be tension force. They are trying to expand, and therefore there will be tension force in these bottom members. So if there are tension force in the bottom members, what will happen? They are trying to expand, right? The bottom members are trying to expand, and the members are giving some reactions to the joints, and the joints will have to do what? They have to maintain the equilibrium, they have to maintain the stability, and therefore the joint will give back a reaction to the member. Okay, so if this member, for example, if this member is trying to expand in tension, it is in tension, it is trying to expand, then the joint will try to maintain the stability. The joint will try to push back the member like this. The joint will try to push back the member like this. Similarly, in this one, in this member, if the member is trying to expand, the joint will push back to maintain the stability, and from the joint, there will be reactions like this. From the joint, there will be reactions like this. So now, this is how we represent the member forces. So it will look like it is in compression, but it looks like this way because we are taking the forces from the joints, because ultimately we are going to write our conditions of equilibrium at the joint. That is why we write the forces with respect to the joint, how the joint is behaving, how the joint is giving the reactions into the member. So this member, now this member, from the diagram it looks like it is giving compression indication, but actually it is in tension. It will be the opposite. So that is how we should remember. We have to understand from where the load is coming, what when it is tension and when it is compression. There we have to understand, and after that we will try to remember. If it is tension, we will express it like this, which looks like compression. If it is tension, we are going to express it like this, like this. For example, if there is tension, compression in the member, for example, in this member, if there is compression, what will happen? The member is trying to contract. So the joint will pull the member to maintain stability. So the force will be like this. Force will be like this. What the joint is doing, joint is trying to pull the member to maintain stability, and we will indicate the member force like this. So in the truss system, there will be no moment. There will be member force in the members of the truss. And this member force will be axial in direction. They may be tensile, they may be compressive, but the moment is not coming because the truss system is theoretically pin connected, pin joint. These are pin joints, okay? So they cannot produce moments. Okay. Let me know if there are any doubts. Then we will go for a little bit of beam. Any doubts? If there, please let me know. Otherwise, we will start a little bit of beam. So these are some types of beam. One is a cantilever here. If it is a cantilever, the one end is fixed and one end is free. We have to remember this. There is no other way. We must know this, and we must remember this if we are civil engineers. So this is going to be cantilever. This is going to be simply supported. That means one end is hinged and one end is roller. And this is called overhanging because we have this portion overhanging from the support. Now this is called continuous. Why? Because this member is supported by more than two supports. Okay. Up to this point, it is supported by two supports. Then if there were no member here, no support here, then it would have been called overhanging, but it is not overhanging. There are another support here, another support here. So this member is continuous. This member is fixed ended. Both ends are fixed. And this member is cantilever or simply supported cantilever simply supported or propped cantilever. Why? Because it is like a cantilever, one end is fixed and one end is roller supported. So it is almost like a cantilever, but here we have a roller support. It's not free like the cantilever. So it is called propped cantilever. Now, suppose we have a simply supported beam. One end is hinged, one end is roller supported. So if load comes from the top, the beam will try to deflect, the beam will try to go down, but due to the supports, it won't go down at the ends. Okay, it will bend like this maybe. At the middle portion, it will bend, but at this point, at this end, and at this end, it won't go down. Okay, there will be no deflection at these ends because of the support conditions. And to maintain that, we have these reaction forces. Because it is not coming down, the beam is not coming down, something is holding the beam. Therefore, we have this reaction here, this reaction here, and this reaction here. So always remember how many reactions are there in the supports and why. Then there are three unknown reactions, and we can write three equations of equilibrium in each beam. Summation of forces along x equal to 0, summation of forces along y equal to 0, and summation of moment equal to 0. Now, you may think that we can write moment equation here also. We can write summation of moment if we say this is A and this is B. We can say that we may write summation of moments about A equal to 0 because it is a hinge point, and we may write summation of moments about B equal to 0 because it is also a point where there will be no moment. And we may get two equations, but it is not true because they both are in the same beam, so they both will be giving us ultimately one equivalent only. Okay, so we cannot write summation of moments about A equal to 0 and also summation of moments about B equal to 0 and expect that these are going to give us different solutions. Okay, they won't. We'll see in calculation later. They are ultimately one single equation. Summation of forces along x equal to 0, 1, along y 1, and summation of moment either MA or either MB. That is one equation. So we have three unknown and three equations of equilibrium. So this is going to be statically determinate. Fine. Then this one. Here we have a hinge support and we have a roller support. In the hinge support, we will have two reactions. In the roller support, we will have one reaction, and this one is overhanging. Okay, simply supported with an overhang. Now, there are three reactions. One member, we can write three equations. So it is going to be statically determinate because the number of unknown is exactly equal to number of equations of static equilibrium. Then this member is fixed here. We have a roller support here, we have a roller support here. So in the fixed point, we will have three reaction and roller support, one reaction each. Total number of reaction is 5. Those are the unknown forces. And then we have one beam. This is one single beam, continuous, but one beam. So we can write three equations of equilibrium. And that means we have more unknown than number of equations of static equilibrium. So this becomes statically indeterminate to the second degree. Okay, degree of static indeterminacy will be 2, 5 minus 3. So this is how we have to calculate static determinacy and indeterminacy in case of beams. Now, before going to a little more complicated calculations with beams and frames, we'll see difference between determinate and indeterminate structure. First thing we know already is that the determinate structure can be analyzed from conditions of statics alone. It's easy to analyze. The unknown forces, what is the meaning of analysis? We want to find out the unknown forces in the structural system. So we can do that with the equations of static equilibrium alone in case of determinate structure. So it is easy to analyze it. But in case of indeterminate structure, we saw that the equations of static equilibrium alone is not sufficient to do the analysis, complete analysis. It is not sufficient. So we have to go for some additional conditions. And those are called compatibility or displacement condition or minimum energy conditions. We'll see what those are. And then we can analyze them completely. So this requires a little more effort. Now, in case of determinate structure, the reactive forces, the RA, RB, etc., they are independent of the member properties like E, A, I. E is modulus of elasticity, A is the cross-sectional area, I is the moment of inertia. So those are the properties of the member. So the reaction forces will not depend upon these member properties. But in case of indeterminate structure, the member properties will have an impact upon the reaction forces. Then in determinate structure, temperature changes do not create additional forces or stresses. Temperature changes will lead to what? The member will be expanding or contracting due to temperature changes, and that temperature changes will not create additional forces or stresses, but in case of indeterminate, they will. There would be no forces or stresses due to lack of fit in case of determinate structure, and lack of it would produce internal stresses in case of indeterminate structure. What is lack of fit? Lack of fit, just like the name is saying, lack of fit means the members, some members are smaller than they should be, and some members may be slightly bigger than they should be. So that is a problem of fit. Okay, it is not properly fit in the structural system. The member which is slightly bigger, maybe we have to apply an additional force to fit it into the structural system, obviously, and that will create an additional stress. If it is smaller, then also we have to do some work, extra work, to make it properly fit into the structural system, and that also going to raise some additional stresses in case of indeterminate structure. But in case of determinate structure, that problem does not arise. The structural system can take care of that. Okay. Now, they do not have any second line of defense. Now, we already have discussed that statically determinate condition is the minimum required condition for balanced structure. For the structure to be stable, the minimum required condition is statically determinate condition. So if it is less than that, the members are less than that, then it is going to be unstable. So they do not have any second line of defense. That is what they are saying. If one of the members fail, the structure would collapse. Because it is exactly at the condition of stability, there is no additional members to support it. There is no redundancy. Therefore, a single member fails, the entire structural system fails. Okay. And in case of indeterminate structure, because we have extra members, because we have these unknown forces, those unknown forces are coming from reactions and members, because there are extra members. That is why we are getting unknown forces more than the equations of static equilibrium. And those extra members will provide us some kind of safety. So even if one member fails somewhere, the structure will not collapse. We will have some time to retrofit it. And that is why in real situation, we will definitely want this condition. We will definitely want additional redundancy. That means we will want extra members, which will give us some safety against collapse. Okay, even though this is going to be a little bit difficult for our analysis purpose, but still we want these extra members so that we are safe from structural point of view. Okay. Then what is compatibility and what are constitutive relationship? These compatibility, constitutive relationship, these things will be required for solving structural systems that are statically indeterminate. So one line, forces should be in equilibrium and displacement of the structure should be compatible. Okay, so I will not go here. We'll come back there after understanding the concept. Suppose this is a structural system. Okay, we have a beam here and there is another beam of smaller cross section. Is the same beam, cross section is larger here, cross section is smaller here, and we have fixed support at this end and at this end also. So A, B, C is the beam, fixed support at A and fixed support at C. So if there are some force in this structural system, so we will expect there will be some stresses, there will be some deflection maybe, but because this joint is fixed and this joint is fixed, there will be no displacement at the fixed points, obviously, right? But there may be some deflection here at this point. Now, this member, if this member expands, this member, it is like this, it comes to this point. And this member, since this member cannot go in this direction, it has to be here only. It cannot go in this direction. So this member has to shorten, obviously. If this member is going to expand, this member has to shorten by exactly the same amount to maintain the condition that this joint is fixed and this joint is fixed. If they do not maintain the condition, then this joint is not fixed, right? Or this joint is not fixed. That's what it will mean. So this is called conditions of compatibility. If this joint is fixed, there will be no displacement here. If this joint is fixed, there will be no displacement at this point. So if this member is going to expand, for example, this member has to contract by the exactly same value. Okay. So delta AB at A, we are saying the deflection of the AB member at A point is 0 because it is fixed. Deflection of BC member at C is equal to 0 because it is fixed. Therefore, deflection of the member AB at B point has to be exactly equal to the portion BC at B point. So that is called compatibility condition. Okay. So compatibility condition represent restriction of deformation at a specific location in the system, just like we saw. Okay, so there is restriction on deformation. If deformation is this much at this point, at the other point, the deformation has to be exactly equal and in the opposite sense to maintain the compatibility condition, to maintain the continuity in the structure. After that, we will require conditions of constitutive relationships. Now, you tell me, what do you know about constitutive relationships? Do you know about constitutive relationship?